Alright, this is day 27 of solving math problems until a Hololive member notices me. So yeah, pretty much here we have another proof, right? We're going to prove the law of cosines. So pretty much what we're going to do, right, is show that we could express our angles, right, and lengths pretty much to the cosine function. So let's go ahead and start by making, of course, a right triangle, the same way we did last time. That does not split in half, but it's fine. Let's just use that as a reference. We just fix this. So we're pretty much given right triangles now, since we made a bisector. And here we are going to have, again, h, and this length right here, right? We're going to ignore, well, we're not going to ignore b. We're going to have, let's say this length is x, and this is b minus x. So with two different right triangles, we could use cosine of A or cosine of C. So we're going to go ahead and use just cosine of A. So we have cosine of A is equal to x over C, right? Since it is adjacent over hypotenuse. And we're also going to get cosine of capital C is equal to B minus x over A. So notice that we kind of have A in cosine of C and C in cosine of A. So what do we do, right? Well, we're going to use the Pythagorean theorem here and say x squared plus h squared is equal to c squared, and b minus x squared plus h squared is equal to a squared. So we have h in both equations, right? Which is going to be important to us in a little bit. So let's go ahead and just multiply by a in this expression for cosine of c. So you have b minus x and a, and x is equal to cosine a times c. So pretty much now we have to plug everything in, right? But the problem is we're not going to plug in bx or b minus x into the second equation because we want to avoid that right now. So I'm going to go ahead and substitute h, but first I have to solve for h, obviously. So we have h squared is equal to c squared minus x squared, and replacing h, we have b minus x squared plus c squared minus x squared is equal to a squared. So with that out of the way, what we're going to do now is expand b minus x squared, which is b squared minus 2bx, and plus x squared plus c squared minus x squared is equal to a squared, where the x squareds are going to cancel out. And since we have x, right, we're going to replace x with c cosine of a, which is going to be b squared minus 2bc plus c squared, or actually I forgot the cosine of a plus c squared equals a squared, which we could rewrite this as a squared is equal to b squared plus c squared minus 2bc cosine of a. And we can also do this vice versa and solve for cosine of c, right? And pretty much here, what we're going to do now is simply just use the fact that this is going to if we swap a, b, and c, we're going to get b squared is equal to a squared plus c squared minus 2ac, and then cosine of b, and then swapping a with c, we get c squared is equal to a squared plus b squared minus 2ab cosine of c. So we pretty much proved the law of cosines for the three cases, right? We just pretty much like did the lazy part of swapping a, b, c at the very end, but we pretty much got all three formulas, right? So we see that our cosine function relates our lengths and angles kind of using the Pythagorean theorem, right? So yeah, pretty much the cosine function helps us find triangles that pretty much we are given, let's say, two lengths and an angle, right? And then we could find the other length, or we could go ahead and find an angle as well. So yeah, that's pretty much it for proving the law of cosines. And yeah, thank you for watching. Hopefully you enjoyed watching this proof, or pretty much like the derivation of the law of cosines formulas, because sometimes it's always good to learn how to derive formulas instead of memorizing them. At least that's in my personal opinion, to be honest. Like, it's always better to learn how to derive formulas and geometrically and also visually look at how you could get at the solution as well, right? But yeah, thank you and bye bye.